Hey gang, welcome back. Okay, so this video and the next video are absolutely crucial. Make sure you have both of these videos down before we go into, a bunch, just a whole slew of examples of walking through NMR problems. This video in particular, we're just going to be talking about terminology, but although that seems a little boring and like mundane and blah, I'm telling you, if you don't know what a bunch of these words mean, or what they designate, NMR is going to be an absolute nightmare. You're going to hate it, and it won't be fun. Not saying it's going to be really fun, but just no fun at all. Okay, so there are really like four bullet points I want to hit and make sure we're totally cool with and understand with after this video is over. So what I want to start first with is this idea of a chemical shift, which you will see designated by the lowercase delta, the little it reminds me of like a little musical note. Okay, so in the last video we talked about how the NMR machine uses this external field and applies it to your sample, and all the hydrogen nuclei in your sample that act as little bar magnets are either aligned with the field or against the field, and they're constantly switching back and forth, giving off energy. Okay, little recap. That energy given off is seen as a frequency measured in hertz, which is designated by Hz, okay? I might actually use a different marker because this one's not that stellar. But the energy is seen as a frequency. Frequency you'll probably see as this funky little script V. It's like a little sideways. And it's going to be measured in the units of hertz, Hz, or if you want to spell that out, Hertz. Just being explicit, because this is kind of like where OChem meets physics. It's a little weird, but okay. So, what is interesting about that is, what do we do with that? It's going to be a number, right? What's it going to be? It might be 340 hertz or whatever. So, what you're going to see, and this is what we'll be moving forward with, is this spectra are just going to look like a line right here, and you're going to have numbers going from 0 all the way to 12, and they're going to be measured with the units ppm. So, okay, what's going on? So what you're going to see are a lot of just lines, bam, 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 and maybe this is at 9.7 ppm, this is at 6 ppm, this is at 2.2 ppm. So what a chemical shift is it is a number where what the machine will do behind the scenes is this scale starts at 0, and this 0 is always measured with, here we go, 4 CH3 is attached to a silicon. And this structure's name is called tetramethylsilane. And I know I'm a little scattered. If I'm a little scatterbrained, I'm sorry. Don't worry, I'll get everything said and recap it at the end to make sure it makes total sense. But your spectrum will go from 0 to about 12 or maybe even beyond, and 0 will always be tetramethylsilane. Okay, so what's a chemical shift? A chemical shift is this value, and you can express it as a mathematical formula. You're never really going to calculate it, but it's basically distance from the CH3 for Si, tetramethylsilane, divided by the strength. Let me make sure I get this right. Oh, yep, hold on. It's basically going to be the, in hertz, the strength of H0, the field in your spectrometer, okay? So, the reason why we use tetramethylsilane is you have to have some type of scale, right? It has to start somewhere. So we pick this, right? We measure its energy value and frequency, right? So then we would find it's 500 hertz, making up a number, right? 500 hertz minus how far away is it from itself? 500 minus 500 is 0, okay? So basically what happens is, we get that resonating energy value in hertz, right? That frequency value. You then compare it relative to tetramethylsilane, right? You'll take that number and you would subtract it from here, and then you divide by the frequency of the field you have going on, and that's how you get this scale. So a chemical shift is just this number. I'm telling you, you're never going to have to calculate it. Really, this is just an exercise in saying, hey, you're going to get a spectrum whenever you do NMR. 0 is always going to be where tetramethylsilane is. All these numbers here are going to be, various areas of your molecule, and they are on this spectrum because we've made this our 0, and it's going to be relative to this. And the reason why your field strength can be whatever, it doesn't matter how strong your field is in your NMR machine, is because you divide by that number, so it kind of normalizes everything. Okay, so what I want to do next, so that's what the chemical shift value is. So now what I want to do is talk about this idea of upfield and shielding and downfield and deshielding. Okay, so I'm going to actually erase this. I'll actually erase this too. And we're going to use some examples. Okay. So, we'll just redraw this. So let's just say we had something like this. We had ethanol, okay? So, you can find tables of chemical shifts because based on different functional groups, you're going to find different values for your chemical shifts. Okay, so let's just do something like this. Okay, so ethanol, right? What you're going to have is we can agree that there are 3 unique hydrogens, right? These hydrogens are all the same, these hydrogens are all the same, and this hydrogen is unique, right? So there's 3 types. There's position A, hydrogen B, hydrogen C, types of hydrogens, if you will. Okay, so when we were talking earlier about H plus protons being their own magnetic field, what happens is in the case of this methyl group right here, right, there are electrons in this bond right here, in this bond and in this bond. So when this NMR analysis is happening in the machine, right, these electrons actually work to kind of shield your H plus bar magnet. So what happens is, that's called shielding, is when there's a lot of electron density near your H plus, near the hydrogen molecule, or atom rather. So what happens is, when you have a situation like that, you tend to be more upfield, which is closer to where the tetramethylsilane, lives, where we've normalized. So a typical methyl group, a typical CH3 like this, will typically be around like 1, 1.3. So if this is 1 in ppm, you typically see a spectral line right there. Okay? Now, here, you see we're closer to an electronegative oxygen. So a lot of electron density is going away from this carbon to here. So what we would say is that these hydrogens are being deshielded. There's less electron density near them because it's going to this electronegative atom. So this carbon is more positive, which means these hydrogens are more, true to themselves, more true H plus mini bar magnets. So what happens is they've been deshielded. They're more downfield. So this will typically, I don't have a sheet in front of me, this will be around, I think, 2, 2.5, somewhere along there, maybe even 3, something like that. And you'll see something like that for these H's. And even this bond right here, this OH bond, this hydrogen has like no electron density. Alcohols end up being around 4, so there's going to be a spectrum there. So the more electronegative, I guess, or the more polar your bond is and the hydrogens you're looking at, the more downfield you are, the more normal and more like non-polar covalent your situation is, the more upfield you are, or shielded. These terms are interchangeable. So downfield means deshielded, upfield means shielded. Okay, I need to do some erasing. We have one more topic to talk about before this video is wrapped up. So, it's this idea of splitting or coupling. They mean the same thing. Okay, so what I want to do is I want to look at, again, we can show this example of ethanol again. And I'm going to draw, again, that spectra we had, starting with 0, ending with 12. Okay, so to kind of use some terminology we've already, gone over, we could locate the various protons in this molecule, right? We know that there are, we look for symmetry or equivalent hydrogens. These are all going to be one signal on the NMR spectra. These will be one signal, and this will be one signal. Okay, so we're going to have 3 signals, right? And so this will be the most upfield signal because it's more shielded. This, since it's attached to an oxygen, an electronegative atom, will be more downfield because it's a little bit more deshielded. And this hydrogen is actually the most deshielded. It will be the most downfield. So the idea we're going to talk about here, splitting and coupling, is that yes, this will be at one signal, but these hydrogens, these little bar magnets, they are going to be affected by the neighboring hydrogens right here. When you have hydrogens like are positions next to each other and we talk to them, we use the word vicinal. So we could say these vicinal hydrogens are going to affect one another. And just for fun, when you have it on the same location, if we were going to talk about these two, you would call them geminal. But just semantics. Anyways, so what are we talking about with splitting and coupling? These hydrogens are going to be affected by them. And it's due to the fact that when you get the resonating effect and the resonating frequency that eventually is what is located on our spectrum, it's because not only do these hydrogens have alpha and beta spins going on, but so do these 3 hydrogens. They have their own alpha and beta situations happening. So it's a little bit of a complex subject, and what you guys need to know to, function and solve NMR problems correctly is what is known as the N+1 rule. Okay? So what we need, so N is just your neighboring hydrogens. So if we were going to, and we're going to start using words to classify what these hydrogens are. So if I'm going to look at this secondary carbon right here, and I want to, correctly draw where, what the signal will actually look like. So the N+1 rule will tell me, all right, so at this location, N is 3 because my neighbors are 3. N+1, this location right here, I'm going to call it locate. I'm just going to asterisk it. The asterisk location is, I got 4 from the N+1 rule, so this is what we call a quartet. Okay? Now, at this location, right, my neighbors are 2, right? So I would do N+1. So if I, my dot location, I got 3, so I'm a triplet. Okay? And that's how you use the N+1 rule. So other, results you can get, 2 is a doublet, and 1 is a singlet. So let's actually look at this alcohol right here, right? So because he is kind of by himself, right, there's no carbons around, this oxygen, right, he is now isolated. So this hydrogen is actually a singlet. So then what you do is you go to a chemical shift table, you locate functional groups and different things like that. You locate the chemical shifts and what's going on, and then from there we would say, okay, I know alcohols occur at about 4 ppm, and I have a singlet, and a singlet is just this tiny little line just like that. It looks like it's just a single peak. Okay? So then what we do next is we would, there's probably some, this is going to be similar to an ether, This is going to probably be around like 2, 2.3, something, or 2 and 2.5. I'm just going to, for simplicity, I'm just going to do, this is 3, this is 2, this is 1. I'm just going to do 2, or near 2, and I have a quartet. Now, a quartet looks like this. You have 2 low ones on the outside, 2 high ones on the inside. And these correspond to how the nuclei spin and pair. And, is it going to be like alpha, 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 or alpha, beta, alpha? How they, basically all the combinations. And this is like how they display themselves energy-wise. That's why you get these energy patterns, these splitting patterns. So, but for us, right, we just need to know their general shapes. So there would be your quartet, and again, I'm not the best artist, this would probably be a lot more compact. Then you'd go ahead and look at the last pair, the singlet, the CH3, it's a triplet. Triplets look like this. one little one big one little one. So I'm just going to go and do one little one big one little one. So this is what the spectrum we would expect for ethanol, right? So to then give you, so singlets look like this. Whoops, go back to the blue. Singlets look like a single peak. Doublets are two equal peaks. And sorry, I'm doing like curlies, but really they just look like this. They're really thin and they have a little bit of area underneath them, like that. Then a triplet is low one, high one, little one. Quartet looks like this. And it goes on from there. If I wanted to do a quintet, right, it would be little one, higher one, biggest one, this one, right? So there's a lot of symmetry involved. You can have sextet, septet, and it all comes back to the n+1 rule. This is your guide when splitting and coupling. Because what people will do is they're going to give you a spectrum, and then you're going to have to say, oh, okay, that's a singlet, that's a doublet, that's a triplet, blah, 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 and you will see how this comes back and helps us in the end. One last thing before we go. The reason why there's this little amount of area underneath there is, and this is a little bit of calculus, don't freak out, I'm not doing any calculus, is that the area underneath this curve is actually corresponds to how many hydrogens this peak represents. So the machine that gives you the spectrum will say, okay, I actually did the math for underneath this curve, the width of this peak, and this corresponds here. The integration number, because it's an integral that helps us do that, the integration number is 1. So then if we looked at our quartet, the integration number would be 2, and the integration number for our triplet is 3. So what's nice is that whenever you look at peaks, you'll know how many hydrogens that peak represents. Okay, we went over a lot in this video. There's a lot of concepts, and I'll tell you what, everything becomes more familiar the more you do problems, the more you use the terminology, and it sinks in a lot more. But chemical shift is how you are represented on an NMR spectrum, where 0 is the tetramethylsilane, and your distance farther downfield is your distance away from it. The more electronegative your hydrogen, the closer your hydrogen is located to an electronegative atom, the more deshielded, the more downfield you're going to be. On the opposite side of that, if you're just in a nonpolar situation, you'll be more upfield. Splitting, coupling, n+1 is your friend. Do the n+1 rule. Figure out, should you have a singlet, a doublet, a triplet, a quartet, a quintet, septet, sextet, whatever. You're really going to be living in the singlet to quartet range. That's what you're going to find most commonly in your problems. Okay, gang, this was a lot. Maybe watch it again if you need it all to sink in. Otherwise, we need one more video pit stop. Oh, and last thing, the integration number is the area that the computer calculated underneath your peak, and it represents how many hydrogens the peak represents. Okay, one more video before we get our hands dirty with some problems. See you then.